we have studied the module number 4. So the module number 4 is nothing but the subsystem design. See, whatever till now we have studied, the adder, multiplexer, implementation of them, all those things. So now we are going to make use of those components and to design an subsystem. Okay. So when you want to design the subsystem, then what are the available platforms are there for the implementation? So all the things you are going to study in this module number 4. So before you go for the design, as I said you, so you need to make some architectural issues. You need to consider these architectural issues during the design process. Okay, so when you make any design, so the following will guide you so that you can minimize the errors which may happen during the implementation of your subsystem or the design process of your subsystem. So what are the architectural issues? So the first architectural issues was defining the requirements. So you need to define your requirements properly. It's not only you need to design the requirement properly, and also you should be very cautious. So what is an constraints you are there for your designs you need to consider. So because based upon the constraints only we are going to change the architectural issues of the subsystem. So therefore the designing the requirement or defining the requirements plays a very crucial steps, and this is the fundamental steps in order to select your architectural process for your subsystem. The second one we call it as a partition of your overall architecture. Okay, so if you have a very complex architecture means then it is necessary for us to divide them into a smaller component, and once you are divided into smaller component, and you should make sure that the division is not dependent between the two subsystems. Okay, so whatever the division you can do it, or whatever the division you are going to take care of the subsystem, the independent dependency should be minimum between one subsystem into another subsystem, so that we can individually test and debug if there is any error occurs in the subsystem method. The next one is the communication path which we are going to develop between the subsystem, because we know that a single subsystem cannot work individually, so it requires a communication with a neighboring subsystem. So how you are going to establish a data paths, control paths, and what are the controlling entity you are going to provide for your subsystems. So all those details you need to take care. The next one is floor planning. So as I said you, the constraints is one of the constraints when you are designing the subsystem is nothing but your floor planning, that is the size of your miniature size of your device. So how much is possible as a designer, we need to minimize the size or the area occupied by the silicon wafer. So when you want to design or when you want to minimize the area occupied by the silicon wafer, especially in the VLSI design, then you need to take care of this floor planning with a very careful manner and with a very effective manner. The next one is the regularity. So this floor planning will be assistive to the regularity of the structure. So why? Because the regularity is nothing but the number of semiconductors what you are going to place in a unit surface area. So the more number of transistor if you place in a unit surface area means then the regularity of the system will be increased, so that you can minimize the miniature size of the subsystem. And the next one is, once you are done with this floor planning, the next one is the implementation wise. So for that you need to use a systematic diagrams or a stick diagrams, so that how the layering architectures will be taken care. And after that, so once you're done with the stick diagram, you will be able to understand so where exactly the layering has to be there, where has to be the contactors, everything has to be connected. So based upon that you can go for the fabrication. Either you go for a PVL fabrication or by CMOS fabrication, depending upon your application where you are implementing your ICs. So based upon that you can go for the fabrication process. So after the fabrication process, then now the next thing is, so we need to check thoroughly so whether the desired output we are getting or not, and if there is any issues is happening. So let's say the one of the issues is heat is dissipating. So if the heat is dissipating more means then it will damage the circuit. So we need to take care of this damage of the circuit carefully, means we need to debug the system and we need to measure its performance for all the unit cases or for all the unit subsystems. Okay, so when you consider this overall architecture issues, so the overall design process we can be considered into two important aspects. So the first one we call it as a partitioning of the system. Okay, so how well you partitioning of your system you do it. So based upon that you can create a best subsystem. The next one is the design simplicity. What you are going to take care in the implementation of your architecture of all the subsystems. So these are the two important parameters, or these are the two important process you need to take care when you start implementing or when you start designing of your subsystems. Okay, so in the next subsequent chapter means the sessions, what we are going to do is, so what are the some of the elements which you are going to use in your subsystems, we need to understand. The first one we call it as a switch logic. Okay, so switch logic is nothing but it is a connection of two nodes. So we will be using this switch logics. Okay, so either we can implement this switch logic by the use of pass transistors, or we can implement this through the use of transmission gates, or we can implement this through the use of a NMOS and a CMOS fabrication process. Okay, so the first diagram what you can able to see it over here is, so the input will be clubbed to output when both the input when all the input terminals are held at high. So means what, the output logic will be designated by the gate voltage what you are applying for this NMOS transistors. So that is nothing but, if the NMOS transistors A, B, C, D, if it is all are logic high means, then the input will be carried to your output. Okay, so that is a pass transistors what we can say in implementation of through the use of NMOS transistors. So the second one what we call it as a, it is a inverters what we call. So the inverter is nothing but the first part of this circuit, it is a inverter, and this again you are converting one with one more inverters. Okay, so therefore what we can say is, so if it is not possible for you to drive the input from input terminal to output terminal, if you have a too much of mediator signals means, then you can divide them. So you can see here A, B, C, D I have divided, and you will be getting the output, and it has been inverted, and from the inverted signal again you are driving some more set of transistors. Okay, so if input cannot be coupled to output simultaneously with a large number of drivers means, then you can make use of this inverted buffering system, so that the input can be clubbed to output with a minimum threshold degradation in the values. Okay, so the next one we call it as a five-way selector switch. So this five-way selector switch, it is also we are going to implement through the use of transmission gates. Okay, so transmission gates we are going to implement. So if you carefully observe over here each unit, so you have a and a bar. So can you able to see here the NMOS, for the NMOS we are giving an A, and the complementary input we are giving to the gate terminal of the PMOS. Okay, so similarly for B, C, D and E. So means what, the transmission gate, it is a combination of PMOS transistor and NMOS transistors, and your V out. So what is your V out? So V out is nothing but what is the logic you are applying for this A terminal. So based upon that, your V in, V2, V3, V4 and V5 will be clubbed to the V out. Okay, so you can see here the V out logic level will not be designated by a VT effect. The V out logic will not be designated by the VT effect. Why? Because since you are creating a transmission gate by the use of NMOS transistor and a PMOS transistors, at any instant of time, either two transistors will be on or two transistors will be off. So therefore, your threshold effect will not come into effect when you are combining the input voltage to the output terminals. Okay, so if this PMOS transistor is 0 means your NMOS will be 1. So since NMOS transistor is 1 means V in will be 0. So when PMOS transistor is 0 and NMOS transistor, when PMOS transistor is 1 and NMOS transistor is 0, so then V in will be 1. Okay, so like this you can able to couple your input terminal to the output terminal sections. Okay, so the next one is, you can see here the NMOS 3 input OR gate we have created. You can see here this is we have done by the use of the NMOS 3 input OR gate. So what is the logic level? That is a Boolean expression for the OR gate is V out is equal to A plus B plus C. So since we can able to create this with the use of CMOS technology, so we can make use of PMOS transistor and as CMOS transistors. So to create a this OR gate level. So we can create either by using this, or we can create either by using a De Morgan's law. Okay, so here we are making use of CMOS transistors, and complement of them also we are making use, so that you will be getting the arrangements of this OR gate. Okay, so this is all related to your logic gates. So the next one we call it as a pass transistor. The next one we call it as a pass transistors. Okay. So why we use this pass transistor is, see, when you directly connect, input terminal cannot be connected to the output terminal directly. Input terminal cannot be connected to the output terminal directly. So therefore what we use is, we use an intermediator called as a transistor to couple or to combine two nodes in a subsystem. Okay, so therefore we use this pass transistors. Okay, so once again I am telling you, this pass transistor is used to couple two terminals or two nodes within the subsystem. Okay, and the voltage degradation in this subsystem will be VT. The voltage degradation means the reduction in the voltage from input to output. It will depend upon the threshold voltage, depending upon the low logic and a high logic. Okay, so now you can see here, when you apply, input terminal is high, and when you give the X is equal to plus 5 voltage means, then you will be getting a output voltage is equal to 0 volts. So now the complement of this, what we can do, we can create it the same thing through the use of this PMOS transistors. Okay, so what you can create, you can see here we are given a input signal from 0 to high, a transition is taking place, and we are creating this with the use of PMOS transistors. Okay, so since we are creating use with the PMOS transistors, so therefore your output will be 0, but it depends upon the threshold voltage what we are giving. So therefore your output voltage will be depends upon this plus 1 voltage. Okay, so means we are taking the threshold voltage as 1 volts in this pass transistor implementation. Okay, so we can create this pass transistor by using two NMOS transistors also. So you can see over here is, so this is a pass transistors what we can create through the use of two NMOS transistors. So if you create your pass transistor by using this method, what happens is, your threshold voltage will be cumulative at the output terminal. Your threshold voltage will be cumulative at the output terminal. Why? Because if you see this, if you apply a logic 1 for this terminal, that is a VDD, so your output at this terminal will be VDD minus VTP, that is a threshold voltage. Now what happens is, that is a propagation voltage what you are going to see it out. Now this is the input for your the next logic. So for this logic what happens is, so this is the input. From this input again you need to subtract the threshold voltage. So therefore what you will be getting is VDD minus 2 VTP you will be getting. So if you combining the elements, more elements in this manner means, then at some instant of time you may not drive the output terminal effectively. You may not drive the output terminal effectively. In such a case what happens is, your output voltage will be 0. So therefore when you deriving or when you driving a large number of elements with this NMOS pass transistors, you need to make sure that the gate voltage what you are giving, it should be very large when you compare to the number of elements what you are combining or cascading in the pass transistors logic. Okay, and we can create one more type of transmission gates, and that transmission gates we call it as a transmission gate. You can see here in the transmission gate, so when the input terminal, okay, when the gate input of this NMOS transistor is 0, so I am talking about this diagram, so the middle one diagram I am talking about here. Okay, when the input to the gate terminal of this NMOS transistor, when the input to the gate terminal of this NMOS transistor is 1, and its complementary will be applied to the PMOS transistor. Okay, so what happens? So the NMOS you are giving 1 and the PMOS you are giving 0. Both the transistor will be turned on. Both the transistors will be turned on. And what happens is, the signal of whatever the signal which is there at the input terminal, so it will be passed. So if you have a plus 5 voltage means it will be passed to plus 5. If you have a 0 means then it will be transmitted to 0. Okay, or else when the input you are applying for your NMOS transistor, if it is 0 and the complementary if you are applying 1 means, then both are turned off, both are turned off. Once again I am telling you, when the gate input for this case, for the transmission gate for the NMOS transistor, when you apply 0, and for PMOS transistors if you apply 1, both the transistor will be off, so therefore the output will be 0. Why? Because the NMOS transistor is not pass logic low high, and PMOS transistor will not pass logic high very well. Okay, so therefore you are supposed to apply an NMOS transistor with a logic high for the gate terminal and PMOS transistor with a logic low at the gate terminal. So if you apply this means, then the output will be coupled to the input terminal. And you can see here, this is a transmission gate symbol. So you can see the transmission gate symbol, it is nothing but it is a combination of two inverters, we can call it as. Okay, so the first gate, the top one, we will be giving a positive voltage, that is a complement of that we will be giving to the PMOS transistors. So the input will be coupled to the output terminal. The next one is the gate logic. The next one we call it as a gate logic. So still now whatever we have discussed, so we have discussed about only the transistors levels. So now we go for what is the effect of this gate terminal. So what happens if I change any modifications to the gate terminal of the logic, we need to see it. Okay, so for that what we have written is, so we have taken a inverter in order to understand the gate logic in case of NMOS transistors and in case of CMOS transistor and in the case of BiCMOS inverters. Okay, so now you can see the first one is the NMOS transistors. So in the NMOS transistor you can see the channel width what we are taking, the width and the length of your polysilicon and the substrate material both are same we are taking in the PMOS transistor, that is in the depletion mode of NMOS transistor, and here also the enhancement mode of NMOS transistors. Okay, so this is the circuit symbol of your NMOS transistors. So where you are going to couple the gate, the output of the couple the gate to the gate terminal of this depletion mode, so it will work like a inverters. Okay, so that is the function what it does by this CMOS gate level logic circuit. Okay, and generally what we call is, so we call pull up network generally in the gate restoration or in the gate logic. Generally what we call it is the top portion of the circuit we call it as a pull up network, and the bottom portion of this circuit we call it as a pull down network. Okay, so generally what happens is the pull up network will drive the output voltage is equal to high, and the pull down network will drive the output voltage is equal to 0. Okay, so this is in case of your NMOS transistors. So the same we can do it in case of your CMOS technology, that is nothing but the combination of your PMOS transistor and the NMOS transistors. So you can see here, if you want to transmit a logic high 1 means at the output terminal, then your PMOS transistor will be activated. If you want to transmit a logic 0 means, then your NMOS transistor will be activated. So it is something like we are using two switches. So that is the top one, it is one switch, and the bottom one when one switch. When both the switches are high, when the switch high, that is when the top switch it is high means, then the output will be connected to the VDD. When the bottom switch is high means, then the output will be connected to the ground. Generally this VSS we will be keeping it to ground. So therefore the Vout will be always, it will be connected to ground. Okay, so we are making use of this gate level as a switch circuit. So for this transistor we can replace it with a one switch, and this transistor we can replace with another switch. So if this switch is closed means, you can see there is a closed path over here, and the output will be combined or coupled to the VDD. And if the bottom switch has been connected means, then the output will be combined to VSS. So generally this VSS we will be taking it as a ground terminal. If the same thing, if you want to go for the BiCMOS technology, so we know that BiCMOS technology, it is nothing but combination of your BJT transistors and along with the CMOS technology. So there also you can make use of this. So the top portion of this we call it as a pull-up transistors, and the bottom portion of this we call it as a pull-down transistors. So why we are making use of this gate restoration or the gate logic to understand is that always when you use any subsystem, when you want to drive from one system to another subsystem, so the data has to be passed either in terms of 0 and 1. So therefore we should couple this 0 and 1 from input terminal to output terminal effectively without any loss in the input sections. So in order to do that, we are making use of this gate level logic. And the symbol, that is nothing but the logic symbol for your NMOS transistors, it has been written it over here. It is 8:1 means, so the channel width, so for the length will be 4 and width will be 1. Okay, so means so it is a pull-up transistors, so because the channel length is more. And the second one we call it as, this is a CMOS technology. So this is how we are going to represent the CMOS inverters. And you can see the CMOS inverters, both means the length and width combination, that is a pull up and pull down transmission ratio, it is 1:1. And for the BiCMOS technology, so we will be representing only with the use of this inverter symbols. Okay, so if you represent your NMOS with the use of this NMOS technology transistor means, then you need to mention that pull up pull down transmission ratio. And here similarly for CMOS you need to mention the CMOS implementation with the length and width combinations, you need to mention it over here. Okay, and the corresponding stick diagram we have written it over here is, so you can see here the overall rating ratio, there is L1 divided by W1 for the top transistors you need to consider. Similarly for the bottom transistors you need to consider, that is nothing but L2 divided by W2 we need to consider for all the cases. Okay, so this is an stick diagram for your NMOS technology. So this is a stick diagram for your CMOS technology, and this is a stick diagram for your BiCMOS technology. So this is a one of the 8:1, that is a pull up and pull down transmission ratio. So you can see here ZPU, it is nothing but LPU divided by WPU, that is a pull up transistor. So you can see here the resistance of the pull up transistors, it is nothing but ZPU into RS. So you will be getting a 80 kilo ohm. So similarly for the pull down transistor, it is a 1:1 ratio. So therefore you got it. Okay. So you can see the power dissipation and input capacitance, it is 1 unit capacitance, that is nothing but CG. Okay. So this is one of the simple NMOS inverters, that is a pull up and pull down transition ratio is 8:1. Okay. So the next one is we called about, this is an alternative for your NMOS transistor, that is 8:1. So like in this manner also we can divide it. So in the previous case you can see here what is the changes we have done, and here what is the changes we have done. So in this case your input capacitance will be 2 CG and your power dissipations will be calculated by using equation. So for the given configurations, so the power dissipation will be 0.6 milliwatt. And these are the circuit diagrams. So what we have used for your NMOS, CMOS and BiCMOS NAND gate implementations. Okay, so this is the BiCMOS NAND gate implementations. I think we all know how we can create this NAND gate implementation. The NAND gate implementation is nothing but AB bar. Okay, so AB bar, as I told you, in NMOS transistor it will be in series. If it is multiplication means, whereas in the case of CMOS technology it will be in parallel for the multiplication, and it will be in parallel in the case of addition, and multiplication it will be in series for your PMOS transistors. Okay, and these are the circuit diagram for your NAND gate by using NMOS. So this is a NMOS implementation, this is a CMOS implementation, and this is a BiCMOS implementation. Okay, so this is the logic symbols what we are going to use it. So here the logic symbol of your AND gate is nothing but AB bar. So here we are making use in the ratio of pull up to pull down transmission ratio, we are implementing in the ratio of 4:1. And this is the circuit symbol. Okay, so this is for CMOS technology and this is for the NMOS technology. and the corresponding stick diagram. So whatever is there, we have written it over here. Okay, so I think we already aware of these stick diagrams. In the module number 2, we have learned how we can create this stick diagram. Okay, and clearly you can see here this stick diagram. Since there is a demarcation line is there, and you have a VSS and VDD is there, and cross multiplication is there, that is a cross section symbol is there, so it indicates that it is a CMOS technology. It is a complementary metal oxide technology. You can see here the top portion it is belongs to PMOS implementation, and the bottom portion it belongs to NMOS implementation. This is the same thing you can implement by using the by CMOS technology by using this stick diagram. Okay, so I request there is no need for you people to just make a note of this. Since you already studied this, you just make use of this. So how we can able to implement these elements, so through the use of this transmission logic gates. Okay. Okay, so this is the BiCMOS 2 input NAND gate. So how you can create this with the use of this contactors. Okay, so this is how you can create a BiCMOS 2 input NAND gate. Now, so now how you can create this the determination of your ratios for the NMOS NAND gate. In order to do that, so we have a highlighted one the diagram, that is nothing but you can see we have a ZPU, that is a pull-up transistors, and that the bottom case we have created a pull-down transistors. So in order to have the effect of this NMOS transistors, so why? Because in the NAND implementation you can see here, so this is the transistor, that is a resistance, that is the impedance what it has been exerted by the depletion mode transistors. So since you had two transistors which are connected in series for the NMOS implementation, so therefore you will be having a impedance of the first transistor and impedance of the second transistor. Since both the transistors were connected in series, so the impedance will be the number of transistors which are connected into in series. So therefore it will be N into ZPD. So N is nothing but the number of elements what you have. So in this case there is only two elements is there. So therefore it will be 2 into ZPD. Okay, so this is how the ratios you are going to determine. It is 1 is to N PD. Okay. So I just want to summarize what and all we have learned in the today's class. So in the today's class we learned about the pass transistors. So these pass transistors are used to connect the two nodes in between them. So we will be using these pass transistors. So these pass transistors can be implemented in several manners. Either you can make use of this only NMOS transistor to implement, or you can make use of the PMOS transistor to implement, or you can make use of the cascaded version of the NMOS transistor to implement these pass transistors. And how the gate restoring means the gate input terminal, how you can feed it, and how the input the transistors will be turned on will be represented in terms of switches. So it is something like if you have two transistors, the top transistors we call it as a pull-up network, and the bottom transistors we call it as a pull-down transistor. So depending upon how you trigger the gate, depending upon that the output will become clubbed. If it is the top transistor, if it is clubbed means then the output will be clubbed to VDD. If it is clubbed to the bottom transistors or the bottom switch is activated means then the output will be clubbed to the ground or a VSS. Okay, so gate restorations we have learned, and we learned about how this that is pull up and pull down transmission ratio how it will be calculated we have learned, and NAND gate implementations we have learned, and this is how the NAND NMOS NAND ratios we can implement through the use of this impedance value. Okay, so this is the circuit symbol how you can create. This is for the NOR gate. So